Good. My name is Hossein. I'm a systems modeling research fellow at the University of Sydney. Today I'm presenting results of my previous research done in the Research Center for Integrated Transport Innovation at UNSW under supervision of Dr. Taha Rashidi and Dr. Nazira Nejad, which was about the application of system dynamics modeling in transport sector. My presentation today is about simulating transport mode evolution, which is an analysis of future trends and policy implication in NSW Australia. So of course, transport sector is one of the most complex systems in the world, in which different factors affecting the transport sector are changing over time, even sometimes day by day. We can see dynamics and changes in fuel prices, which are going up, and air pollutions, populations, especially in cities. GDP increases over time and is being affected by external events like COVID-19. Urban areas, especially in NSW, is expanding, which causes more demand in transport in cities. Regarding technological factors, we can mention that EV's market share has not sharply gone up here in Australia. In general, the fuel efficiency of ICE engines are not going up. It's like they got saturated. And at the same time, personal vehicle size are going up and the congestion in cities are going up day by day. So considering these dynamics and changes over time, which it's a bit difficult to forecast what would be the future value of these parameters and these variables over time. Our main question here is that what is the long-term trend of private personal vehicles versus public transport use over time? How the dynamics of urban transport mode choice impact this trend, and what factors impact this transport mode choice? And again, regarding that uncertainties, how different scenarios, uncertainties can impact the trend over time. In this slide, I'm trying to show you the current situation in NSW based on the latest data published by Australian Bureau of Statistics. In the left top figure, we can see the average transport demand per capita for cars by orange and for cars by blue, the right axis, and for buses in orange and the left axis. We can see that the average is almost a line and does not change over time. This graph is about 1 million vehicle kilometer per person per year, which shows that the demand per person is not increasing or decreasing considerably. But at the same time, we can see that the demand per person for buses are around 80 million, but for personal cars is about 7,000 million. And which this shows the dominance of personal vehicles as a main transport mode here in NSW, and the far distance between cars and buses, which is the main thing that we are focusing here. The middle figure shows the number of buses and cars. They are growing almost in a linear way with a similar slope, but it seems that we need more buses to change that story. At the same time, we can see that the average kilometers traveled by cars and buses are a bit going down. So this shows that with the current trend, the dominance of cars is not going to be changed over time. At the same time, the right down figure shows that the trend in GDP increase is more than trend increase in population. Therefore, we will have more GDP per capita in future. And we know that the GDP per capita shows an index for new sales of private cars. So it seems that the economic and social situation in NSW also supports that the personal cars will be the dominant transport mode, and the difference between private and public sector will remain the same. I'm not going to review the literature completely, but one of the main researches about application of system dynamic simulation modeling in transport is Astra model, which published in 2010 in this paper, but it applied since 1997, covers 27 countries and different subsystems, as you can see here, the population sector, economy sector, trade sector, which completely give us the demand, transport itself, environment, and vehicle fleet. And also, this model provide good sensitivity analysis tools and gives us a platform to analyze policies like standard setting, infrastructure pricing, fuel taxation, etc. You can access the model and change parameters, run simulations yourself. But here we like that research, we use system dynamics. The main steps based on Sterman is first problem articulation and dynamic hypothesis, and then formulation of a qualitative model and then a quantitative mathematical model. The qualitative model is presented in terms of causal loop diagram, and the quantitative model is in form of a stack flow diagram, which includes the equations. And then we will go through testing, verification, and then validation of the model. At the end, we will evaluate some scenarios here. Different data sources are used in this model from different agencies and organizations in Australia. I'm skipping that. The base model we used to develop our simple model is Polya technology competition model, and we based on that basic model, we derived some initial causal loop diagrams and then aligned them with the literature and revised them with some domain experts. We considered buses and cars as representatives for public-private transport mode, and assume that what we found at this study about private or about cars and buses could be generalized for private and public transport modes. Historical data used from 2010 to 2021. Simulation starts from 2010 to 2030, and scenario simulation starts from 2024. We used VenSim software for model development and simulation. So in this slide, I'm presenting the structure of model. These are causal loop diagrams. The left figure shows the CLDs for cars, the dynamic of utility for cars, and the right one shows the dynamic of utility over time for buses. They're almost the same, but and they have inputs to each other. I'm explaining the car ones here. Based on the population, we have the transport demand, which is calculated in the model by the per capita demand and the population. And based on the relative car or bus utility, this total transport demand is divided to personal car kilometers traveled or bus kilometer traveled. It should be noted that we used only the data for bus and cars to calculate the transport demand per capita. So other transport modes, the data for them is not included here. Based on the personal car kilometers traveled, we can calculate the kilometer traveled per capita, which shows, which is an index for a habit of using your own car or not. So if someone uses public transport more and more, then it will gonna be the habit of public transport for that person. Then we have personal car utility, which is a function of that habit, a fuel price, toll fare cap per vehicle, and also average flow, which is a variable considered here to include the congestion of urban areas in the model. And then based on this personal car utility and bus utility, which is calculated on the right part, then we will have relative car utility, which is calculated based on a logit function, which closes this loop. And in the loop above, based on GDP and population, we have a GDP per capita, which determines the number of personal cars, and then the average density reduces the flow. One of the things that happens is that based on this flow, more roads will be constructed to balance the traffic. And the dynamic for the buses are the same, with minor changes like number of buses, which is not calculated based on GDP per capita bus as a share of GDP. And also here we don't have, for example, toll fare cap. We have bus fare per travel, which less fare, more utility for users. A number of bus stop, more bus stop, more accessibility of buses. So based on that qualitative model, we constructed a stock flow diagram of the model. We considered the exogenous dynamics like population, GDP, toll fare, and bus fare as a simple annual gross ratio multiplied by the GDP in that year, calculating the changes over time. This is the same for fuel prices. In the heart of the model, the relative car utility, for example, is a logic function of car utility and bus utility. And car utility is the weighted average of affecting factors, car utility factors over time. And the summation of weights will be 1. For example, total demand is total demand per capita multiplied by population. And the population, as I said, is simply calculated by a simple gross ratio, yearly gross ratio. This one is used for number of new cars, which is shown here. The change of number of cars over time is calculated based on this saturating function, which uses GDP per capita.
Excuse me, Hassan, if you can kind of speed up.
Okay, thank you. We can see the model validation here in this slide. I'm skipping explanation on that. This shows the result in the base run. We see that the the personal car kilometer traveled shows 14% increase during the period of 2024 to 2030, and buses show 46%, but the kilometer traveled is far less than personal car kilometer travel. I analyzed the model in different parameters to find one of the variables that can change the behavior, so we can kind of stabilize the growth of personal car kilometers traveled. This is one of them. If you remember from here, we have a yearly gross ratio for fuel price. If we increase that ratio up to 30% in 2030, which means 0% in 2024, and 30% increase on the annual growth of fuel price in 2030, which is not a huge increase, we can see that the behavior of personal car kilometer traveled is going to be kind of saturated. It is still the main and dominant mode of transport, but we can see a sharp increase in bus kilometers traveled, which is more than 100% increase. So just trying to make the conclusion, we saw that the current policies in NSW, business as usual, is not going to change the situation. If we consider slight increases compared to the historical trend in the effective factors on utility of cars, then we will see that the behavior of the agents in the system will change over time. I am now working on adding energy and emission to this model, and also analyzing more different and interventions and scenarios. But this model could be developed to consider different public transport modes and different private personal transport modes as well, and different type of transport demand like passenger, freight, etc. And also an economic section could be added to model to analyze the cost and benefit of an intervention or scenario. And thank you so much for your patience.
Okay, thank you so much. Let's see if there's any question. I don't see anything in the chat box. Also, we have Q&A.
Can I ask something?
Yes, sure.
Okay. Yeah. Hi, I'm Eugene Kim. Actually, your research is very interesting to me, and especially actually, I'm new in system dynamics model, so I'm curious about it. So I'm very impressed you make the causal loop in this model. So I just asking, how can you make the causal loop? Is it based on your domain knowledge, or is it constructed by data-driven method or something?
Yeah. In fact, in the modeling procedure, we first define the problem and define the dynamic hypothesis, which shows us how for example, in this case, that dominance of personal cars changes over time. Where this come from, we review the literature to see what factors affect the dynamic. We do interviews, semi-structured interviews with experts, and we analyze the data, especially over time analysis, behavior over time graphs, etc. And causality analysis, for example, Granger causality test, for example, or windowed correlation, to see which variables, changes in which variables causes the change in other variables over time. This gives us a knowledge about hypothesis, that what drives the change over time. At the same time, I have used a basic model of Polya, which is the literature and includes the main dynamics in it, and customize it based on the data in NSW.
Oh, yeah, it's cool. Thank you.
You're welcome. Thank you.
Also, we have one question from Nasser in the chat box, and Nasser has mentioned, okay, as you mentioned, the car demand is about 100 times greater than bus demand. So in your opinion, how can we tackle this issue and reduce the demand of cars or increase the demand of buses?
I think the thing is not that we can have buses as the dominant transport mode. It is not gonna be the case, but at least we can stabilize the behavior of growth in cars. So we will not see the cars less than buses, but we can see that the number of the curve in number of cars, or the better than that, the vehicle kilometers traveled to be stabilized over time, which then, regarding the increase in fuel efficiency and the increase in share of EVs, then we will control and even reduce the pollution, air pollution, and fuel consumption, etc.
Okay, great. Thank you, Hussein. Well, Hussein very independently actually drove this research and still is driving. So thank you so much. Let's just jump into the next presentation by Eugene.